Okay, hello everyone. Welcome to the third lecture in Calculus 1. So today we'll finish up what we started with in the last lecture, that's talking about functions. So what remains to be talked about is the properties of real valued functions. So real valued functions, so I'm going to use this notation R underscore V to denote the set of all real valued functions. And what are these? These have some domain contained in R and they take real values. So every real valued function will have something called a natural domain. So what is that? That is the largest subset of R on which the function f is defined. Okay. So in other words, so D is going to be a natural domain if if there is some point outside D, then f is not defined. Okay, so that means that D is the largest. So D contains all the points at which f can be defined. So examples of natural domains. So any polynomial function will have R as its natural domain. You can see I can plug in. So given any polynomial, I can always plug in any value of R. And so f of x is well defined in that case. An algebraic function of this form, which is a ratio of two polynomials, need not be defined at all points of R. For example, this one is not defined at 1, so I have to find the natural domain. All I have to do is simply omit 1 from R. This is the natural domain. So it's pretty easy to determine the natural domain just by inspection. Sin x, we know its natural domain is R. It's defined everywhere. On the other hand, if I look at the function which is the reciprocal of sin of x, then its natural domain is going to, so I have to be a little bit careful because here the denominator, whenever it vanishes, function is not defined. So that means to find the natural domain of this function, I have to omit all the points at which sin x is 0. So it's going to be R minus all integral multiples of pi. So next up, we'll talk about algebra of real valued functions. That is, once again, something you have already studied in your high school. You can add, subtract, multiply, divide to real functions as if they were real numbers, right? So there's some sort of, so that's called algebra, having addition, multiplication, all these things. Okay. So what makes it possible to add to functions, real valued functions, to get another real valued function is the idea of pointwise operation. Okay. And the fact that you can add, multiply, subtract, or divide two real numbers. So this algebraic structure of the set of real numbers in turn gives an algebraic structure to the set of real valued functions. So these are two different entities. Okay, one is a set of numbers that have some algebra that is leading to an algebraic structure on the set of functions. So this idea, let's talk about this. So suppose f and g are two functions with domain d1 and d2. So this need not be natural domain. I can have some smaller domains as well. So depending on the context, I can have different domains. So f and g are two functions with defined on domains d1 and d2. Then how can I add, multiply, subtract, or divide these two functions? So first of all, to make sense of any of those operations, I have to restrict my attention to those values of the domain which are common to both f and g. That means I have to look at d1 intersection d2. So on this domain, both f and g are defined. So if x is coming from this set, then it makes sense to talk about both fx and gx. Okay, so first of all, addition. So h is defined from this d1 intersection d2 to r as simply h of x equals to f of x plus g of x. So this is what I meant when I said pointwise. So why see this addition, basically we are adding two real numbers. So basically, how am I assigning, or how am I defining this function h of x? By looking at the pointwise behavior of f and g. And see, when I evaluate f and g at x, I get real numbers and I can add to real numbers. So I'm evaluating at a point and adding. So that's sometimes called a pointwise operation. Okay. So I'm using this pointwise addition here to define my function h of x. Well, by doing this, are you getting a function that you can check? So for example, we can do this quickly for this one. For the remaining ones, you can check on your own. So this indeed defines a function. So what we have to do, we have to take two different points or equal points, x1 equals to x2, and I have to show that so this implies, or then h of x1 must be equal to h of x2. So why is this? So if x1 equals to x2, so f and g are already functions, okay? Which means this rule already, so what this rule of being defined as a function already holds for f and g. So therefore, for example, x1 equals to x2 means f of x1 equals to f of x2. Similarly, g of x1 equals to g of x2. Therefore, h of x1 is f of x1 plus g of x1, which f of x1 is f of x2 and g of x1 is g of x2. Therefore, that is also equal to f of x2 plus g of x2. And by definition, that is equal to h of x2. So therefore, we have this condition going. So therefore, this function is defined. So h is also a real valued function. It has a domain subset of R, and that is, so this function h is denoted by f plus. So this is the sum function of two functions. So once again, this is not a real number. Once you evaluate this at a real number, it's going to give a real number, which is the sum of fx and gx. But is this really a function f defined to be f plus g? Similarly, you can define product. So pointwise product. So this product function, once again, it has to be defined on this common domain. So p of x is going to be fx times gx. So pointwise product. So this so p also becomes a real valued function on this domain. Next, let's try to define the quotient fx of f by g. So fx by gx. So my function, quotient function qx equals to fx over gx on this domain. So once again, I'm defining pointwise, and I'm putting a red circle over here. We have to be a little bit careful in this particular case, because there could be some points here where gx vanishes, and if that means gx becomes equals to 0. And if gx is equal to 0, then this is not defined. So I have to omit those points. So omit all those x's from d1 intersection d2 for which gx equals to 0. Then fx over gx makes sense, because once again, quotient of real numbers makes sense. So this is a pointwise division. So pointwise division leads to this quotient function q, which we are going to call f by g. So examples, so fx, I'm taking it to be square root x, gx sine x. So f plus g, f g, f over g. So first of all, let's talk about f plus g and fg. So the sum function will be defined on the intersection of domains of these two functions. So this has domain as its domain all the non-negative reals, and this is all reals. So intersection is just a non-negative reals. So this set of non-negative reals is going to be the common domain for both f plus g and fg. In fact, in this case, this is the natural domain because these are natural domains. For f by g, once again, we have to be a little bit careful. It's square root x over sine x. So I can just make sure that it's the set of all non-negative reals, except that I have to omit all those points where sine x vanishes. So simply subtract all the integral multiples of pi. This is a subtraction sign. So the natural domain for f by g in this case is going to be this. Next is graph of a function. So it's important to distinguish between a function, which is just a rule, from its graph, which is, really the graph is set of pairs. So once a function is given, For each input, I'm going to get an output. So I'm going to pair up that input with its corresponding output. So that's going to give me a product. Okay, so this is so we can think of this, if you know about Cartesian product of two sets, it's pairing up of elements from two different sets. This is the Cartesian product of the domain and the range. So that gives you a graph. And you can see for this, since this function is real valued, this pair is always an element in R cross R, which is the Cartesian plane. Okay, so that means I can plot these points on the Cartesian plane. So along the x-axis, obviously, I'm going to plot the inputs, and along the y-axis, I'm going to plot this function values, fx1, fx, and then connect those dots to get the graph of a function. Okay. So the graph need not be continuous. I'm just giving an example here. Okay, so in the previous lecture, we talked about how to recognize whether a given rule is a function. So now suppose I give you the graph of a particular rule, okay? And by looking at the graph, can we say if the given rule is a function or not? It's obviously possible. So this is something called the vertical line test. So suppose I mean, some rule, when I plot that on the XY plane, I end up getting something like this. Okay. And so is this the graph of a function? That's the question. So it can't be. That's because, you know, so if it were a function, any vertical line through the graph of a function can intersect the graph at exactly one point. Why is that? Because if it intersects, if a vertical line through that graph intersects at 2 points, that means for a common input, for the same input, I'm having two different outputs, which defies the basic law of being a function. That is, every input can be assigned to a unique output. But so if the graph fails the vertical line test, then the graph is not that of a function. For example, circle is not the graph of a function, although it is the graph of an equation. Okay, so equations are very closely related to functions, but it's certainly not a function. So the graph follows a rule. That means x squared plus y squared, for example, equals to 1, say. It follows a rule, but it's not a function. So basically, this you could think of as the graph of the rule y equals to plus minus square root 1 minus x squared. So this represents of two signs over here is what is making it not a function. However, if you remove certain parts of the circle, you can get a function. For example, the semicircle, although it doesn't look like it, a semicircle. So if you remove the bottom part of the circle, you get a function. So that means I'm just taking the plus sign. Similarly, the same function will work here if I restrict. So each part of the circle in a given, so a part of the circle in a given quadrant is going to represent a function. That's because, once again, it passes the vertical line test. And equations can be similarly given. So this equation, for example, is going to work here as well, except the domain has changed. So from -1 to 1, we have from 0 to 1. Similarly here, you have to change the sign and domain. So all of these are functions. Next one, can we identify an injective function from the graph of, okay. So this is called the horizontal line test. So notice that if we have an injective function, any horizontal line can intersect that graph at most 1 point. Why is that? If suppose a horizontal line intersects the graph of this function at 2 points, this loses the property of being injective, namely because for two different inputs, I'm having the same output. So fx1, fx2. So these are the y coordinates of this point, and they're, because of this horizontal line thing, they're the same. So two different inputs leading to one single output, that means the function is not an injective function. So if a function passes the horizontal line test, then it's an injective function. For example, monotone functions are typical examples. I mean, every injective function is a monotone function. For example, so say moment it decreases, so it has to be either continuously increasing or continuously decreasing. So if it suddenly dips down, then once again it is going to fail the horizontal test. So injective functions are always either increasing or decreasing, or in other words, they're monotone functions. So that brings us to the definition of monotone functions. You already know. So if monotone functions are, they either keep decreasing, or I mean, they can keep increasing or keep decreasing kind of functions, right? So a function is increasing on a domain if, so we're just trying to say it mathematically. If x1 is a point in the domain that lies to the left of x2, that means x1 is less than x2, then fx1 is strictly less than fx2. So increasing, I'm using increasing for strictly increasing functions, okay? And the functions that are not strictly increasing, I'm going to use the term non-decreasing here. So x1 less than x2 implies fx1 less than fx2. F is decreasing if this thing, so if f is decreasing, then this direction has to be reversed. So as x1, as the domain values increases, the range values decrease. So that means x1 less than x2, but then fx1 less than fx2, bigger than fx2. Function is non-decreasing. So non-decreasing is pretty much similar to it's pretty much similar to the increasing function, except that in place of the strict inequality here, we have a less than equal to. So this means I should have something like x1 less than x2 should imply for a non-decreasing function that fx1 is less than equal to fx2. So this is an example of a non-decreasing function. See, it's not strictly increasing. So it's strictly increasing somewhere, then it plateaus for a while, and then it increases again. So but it never dips, right? So it's non-decreasing. So similarly, we can define non-increasing functions in this fashion. Restricted domains, we have already come across this term. For various reasons, you might want to restrict the domain to a domain of a function. Instead of working on the natural domain, you would like to work on a much smaller domain. For example, yesterday in the last lecture, we did this with sin x in order to define sine inverse. Similarly, we did something with the function x squared to define the function square root of x, its inverse, right? So sin x, you can restrict the domain for several other reasons. For example, this is a graph of the function sin x, and since this is a periodic function, it's enough. So once I have this piece of the graph, I can completely analyze the function. Okay, because after this chunk is going to repeat again and again and again. So there's basically no point in, I might as well focus my attention on this particular strip from minus pi to plus pi. So that's a restricted domain. So we end this lecture with this notion of equality of two functions. So suppose f is a function from D1 to R, and G is a function from D2 to R. So these are domains of f and G. And suppose there is a subset of D1 intersection D2. So D1 intersection D2 is, once again, the set of, it's a common ground for both f and G. So f and G both are defined on this set. So suppose there is a subset, suppose it's, so it's given that there is a subset D of this D1 intersection D2, where f and g agree or they coincide, then we're going to say that as a function f is equal to g on D. See, D first of all can be a domain for both f and g because it's a subdomain of their initial domains D1 and D2. So we might as well study, we might as well as consider f as a function from D to R. Similarly, g a function from D to R. So if on D, f and g are equal, then we say that as functions on D, they're the same function. So with some examples, things will be clear. Sine x and x. So as function sine and that identity function x, they're going to be equal functions on, if I restrict my attention to the set 0. See, on this set 0, both have the same value. Both take the same value, right? So sine, these two functions. So this is a very bad example. This set is too small. So let's try to find examples of two different functions which become equal on an infinite set. So that's why I'm looking at two functions. So first function is sine of pi x, and the second function is fractional part of x. So this is x minus floor x. So this is a fractional part of x, if you recall from high school. So notice that on z, both of them are identical. So both of them are basically 0. Sine of pi of any integer is, so any sine of any integral multiple of pi is 0. Similarly, if x is integer, then its fractional part is 0. So yeah, so as functions, this fractional part of x and the sine function, they're identical functions on Z. So I'm not good. So whenever say I have to study the sine function on Z, I might as well, instead study the function x minus this whatever the fractional part of x. Okay. Let's make things slightly more interesting by, you can have two different functions agreeing on an interval even. So say fx is equal to 0. That's a constant function, okay? And gx equals to the floor function. So notice that on the set clopens, or closed at 0 and open at 1 interval 0, 1, these two functions are going to coincide because floor of any value here is 0 and f of x also takes value 0 here. So f is equal to g on this term. So you can have different functions, they're behaving identically on this. So then we say that those two functions are equal. So these were some of the important notions from the theory of real valued functions, just the basics though. In the next lecture, we'll start talking about subsets of real numbers, another important chapter. Okay.